thought I'd make some videos just to go over the waves topic and just for your revision for your checkpoint assessment on Tuesday. This is very general waves, so it will be probably both foundation and higher. So you can pause the video at any point to make notes, and you might want to make notes of what I say sometimes as well. So I just thought I'd flick through my PowerPoints and then you can make any notes that you want, and then I might do some writing on the visualizer. So the first part of waves is to do with wave structure. So let's have a look at this. So the two types of wave that you need to be aware of are the overarching sort of forms of waves are longitudinal waves and transverse waves. So you can see here at the top you've got a longitudinal wave, and if you watch one particle they go forwards and backwards, okay? So we would say that the oscillations or the vibrations go forwards and backwards. And if you look at the way the energy is moving, so if you follow one of the compression points along, you'll see that the energy is moving to the right. So these are in the same planes. The oscillations go forward and backwards and the energy goes forwards. We say that they are parallel to each other. So the vibrations of the particles are parallel to the direction of energy transfer, and it's the energy that the wave is transferring. If you look at the transverse wave below, if you watch a particle, it moves up and down, okay, but the energy moves forwards. So what we say in this situation is the oscillations move perpendicular to the direction of energy transfer. So on the next slide there's actually some definitions you can write down if you want to. So yeah, transverse waves, the vibrations move up and down and the energy moves forward. So we say the vibrations are at 90 degrees or perpendicular to the direction the energy travels. And examples of that are all the electromagnetic waves, which include light, infrared and ultraviolet. Okay. Longitudinal waves, the vibrations move backwards and forwards. So we say that the energy moves forwards, so they move in the same direction as the vibrations or parallel to. Okay, so an example of that is sound. So I'm speaking now, so I'm making the particles in front of my mouth vibrate backwards and forwards, but the energy is moving forwards to my microphone. You need to be able to label the wave. We're going to label a transverse wave in a second. But this is a longitudinal wave, so you can see here you've got areas of compression, okay? So that's, this is like a slinky example. So where the particles are close together, that's compression. And you call where they're spread apart rarefaction, okay? And the size of the wave would be from the middle of one compression point to the middle of the next compression point, and we would call that a wavelength, one wavelength. So if you're asked to draw a wavelength on a longitudinal wave, find the compressions, draw a line down the middle, one there, and the wavelength is the distance between them. Okay. So we're going to just label a transverse wave now. So I'm just going to change to my visualizer. So when you label a transverse wave, it looks like a wave that you might see on the sea, okay? So often it's on a graph, and on the x-axis of the graph you would have time. So I'm just going to draw my wave here carefully. So the first thing that you need to know that you might be able to ask to draw is the amplitude. Now the amplitude of the wave is from the bottom or the top of the wave to the middle. Lots of people draw it all the way, but it is either from the peak to the middle or the trough to the middle. So this is called a peak and this is called a trough. Okay, and those distances there in black, they are called the amplitude. And if you think about it in terms of sound, it's actually the volume of the sound, okay, or the brightness of the light, etc. So it's how loud the sound is, the amplitude. What you might also get asked to draw is the wavelength. So the easiest way to draw the wavelength is from peak to peak or trough to trough. Now I've only got one trough on here, so I can't do trough to trough. So draw a line from the middle of each peak and across. I'm going to call that number 2, and that is our wavelength. Okay, and the symbol for wavelength is an upside down Y. It's called a lambda. Okay, wavelength. Now, some other things that you might get asked about a wave would be the velocity. So the velocity of a wave is its speed. So it's given the symbol V, it's measured in meters per second, and it is the speed of the wave. You might also get asked about the frequency. So the frequency of the wave is given the symbol F. Okay, it's measured in hertz, Hz, and it is the number of waves per second. And there is an equation for it which you'll be given, which is 1 over t. And this t is called the time period, and the time period is the time for one wave. So t in that equation, so t, this t here, is called the time period. Notice it's capital T. It's measured in seconds, okay, and it is the time for one wave. So that is how you would label up a graph and some of the key terms, label up a wave and some of the key terms associated with that wave. Okay, just going to then have a look at the next bit. So the next thing you'd have to be able to do is then use this frequency, speed and wavelength in an equation. So there's 2 equations you can use. You can use speed equals distance over time, and you can use wave speed equals frequency times wavelength. Okay, so all you need to do is look at the question and substitute in the values that you know, and then you need to just rearrange to find the value that you want to find. So let's look at this equation. Here we've got what speed does a wave of wavelength 2 meters and frequency 3 hertz travel? So you're just going to do the frequency, which is 3, times the wavelength, which is 2. So 3 times 2, which gives us a speed of 6 meters per second. So that's fairly straightforward, and that would be on foundation and higher. Okay. Example 2, you've got a wave speed of 300 meters per second. This would be on foundation and higher, but it's a little bit harder because they give your frequency as 3 kilohertz. Okay, so what is the wavelength of the wave? So I'm going to do that for you with my visualizer. So there's the values that I've taken. So my velocity is 300 meters per second. My frequency is 3 kilohertz. Now 3 kilohertz is 3,000 hertz. Then I can use my equation. So wave speed or wave velocity equals frequency times wavelength. Sub in the values that I know. I know my velocity is 300. I know my frequency is 3,000 times my wavelength. And I need to find my wavelength. So I'm going to divide both sides by 3,000 to get rid of the 3,000. They cancel out and I have 300 over 3,000, which is 0.1. Okay, remember that upside down y is lambda, and that's wavelength. So lambda is 0.1 meters. Again, a question that would be on foundation and higher could be, but the killer makes it a little bit harder. So it would probably be out of 3, and you'd probably get a mark for changing the killer into 3,000. Look at the next one. So the next question says, the speed of a wave is 300 million meters per second. So that is the speed actually of all electromagnetic waves, which we're going to look at in a bit. It says it has a wavelength of 300 meters. What's the frequency of the wave? So back to the visualizer, I've just written down the values here. So we know our velocity is equal to our wavelength times our frequency. So sub in the values that we know that the velocity is 300 million meters per second. Now you might get that in standard form. So if you got it in standard form, it would look like this, 3 times 10 to the 8. You'd get that maybe on higher. 3 times 10 to the 8 means 3 with 8 zeros after it. Okay, so 300 million equals our wavelength, which is 300, times our frequency. I'd like to find frequency, so I need to get rid of the 300. So I'm going to divide both sides by 300. So I've got 300, I've written that wrong, I've done 3 million there. It's got 8 zeros. Did you notice I've done it wrong? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so 300 million. And dividing both sides by 300. So those cancel, and then I just need to sort this out. So they cancel with that cancels with that. 3 divided by 3 is 1. So I get 100 F. Is that the right number of zeros? 1, 2, 3, 4, 5, 6. 1, 1, 2, 3, 4, 5, 6, 1. Yeah, so you can do it on a calculator. It's a million. You might get asked to put that in standard form if you're doing higher. So 1 with 6 zeros would be 1 times 10 to the 6 hertz. Okay? So this is more of a higher question, although you can get it on foundation. It's just that that would probably not be in standard form. Okay. Right. I think that's it for this section yet. So just press pause and we can look at that. So we just need to take a quick look at this. This is actually just higher. So if you are doing foundation, you can just skip to the next chapter. But we just need to look at waves that are used for exploration and detection. So one type of wave that we use is a sound wave that we use for looking at things is ultrasound. So these are actually ultrasounds of my daughter. So one is a 2D image and one is a 4D image. But what they use is sound waves which bounce off the different layers within the body, and you can see an image. So the thing that's important for this, and actually there's a better, well actually ultrasounds are used for lots of things, so not just looking at babies, you can see like the image there, it's showing a heart beating. But this is the main way that we use ultrasound, so working out distances to things. So I'm going to show you how to do this on my visualizer, but I'm going to write down the values as we go along. So it says it takes a pulse of ultrasound 5 seconds to be emitted from the boat and then return. And it says the speed of sound in seawater is 1520 meters per second. How deep are the fish? Okay, so I'm just going to show you my visualizer now and we can have a look. So I wrote down that information. So basically we've got a boat on the water and it's looking at some fish down here. And it says it takes 5 seconds for the wave to come down to the fish and then get back to the boat. Okay, it would like to know how far away the fish are. So we're going to use speed equals distance over time. Okay, and we'd like to find distance. So we can sub in our values that we know. So our velocity is 1520. We don't know the distance and the time is 5. Okay. So what we can do then is I've got to divide by 5 here. So I'm going to multiply both sides by 5. So I get 1520 is D times 5 over 5. Like that. So I've multiplied both sides by 5. I didn't do that side. There you go. and these two cancel, so I know that the wave travelled 5 times 1,520, which is 7,600. Okay, but that's how far the wave travelled down and back, and I need it to just be down because I want to know how far the fish are away. So what I need to do then is divide it by 2 to get my actual value of how far away the fish are, and the fish are 3,800 metres, which is 3.8 kilometres away. Okay, so I mean, ultrasounds work in exactly the same way, it's just that the speed of sound is different. Okay, so that's how we use waves for exploration. I think that's it. And then you've just got earthquake waves. So just so you can see this, I'm not going to play this video, but some types of waves in the earth can't travel through liquids. So this area of the earth here is the liquid outer core. So S waves can only travel through solids in earthquakes. So they can only travel through this part. Whereas P waves, primary waves, can travel through liquids as well. So what they discovered was when there was an earthquake, you were getting these S waves here, but you weren't getting them here, but you were getting P waves. So what that told scientists was that there must be a liquid inner core in the earth, which determined the fact that, they determined the fact it was liquid because the P waves could travel through it, but S waves couldn't, so it must have been a liquid. So we're going to look at the electromagnetic spectrum now, which is higher and foundation. So you need to know all the parts of the electromagnetic spectrum, you need to know the order of them, you need to know the uses of the different parts, and you need to know the dangers. Okay. You don't need to remember the frequencies and the wavelengths, although I'll put them in, but you do need to know which one's the biggest and which one's the smallest. So this is the electromagnetic spectrum. It's a very special family of waves that are made up of an electric field and a magnetic field. And they follow that same equation we learnt before. Okay, but they all travel at the same speed. Okay, so a question might say, name something that's the same about all electromagnetic waves, and you would say they can all travel at the same speed, which is 300 million metres per second, or 3 times 10 to the 8 in standard form, or 3 with 8 zeros. Other things that they all can do is they can all travel through a vacuum, and we know that because the sun produces them all, and we feel all these types of radiation from the sun, and between Earth and the sun is a vacuum, and by vacuum I mean a place with no particles. So unlike sound, which cannot travel through a vacuum, so we can't hear the sun, we can't hear the noise that the sun's making, we can see these other types of the spectrum. Now, the one with the longest wavelength, so the most spread out, is radio waves, and the one with the smallest wavelength, the longest wavelength is radio waves, and the shortest wavelength is gamma. And if I just show you on my visualizer what that looks like, the red end of the spectrum, the wavelength, this is more pink, but you get the idea. Just get my thing out. So the wavelength is nice and spread out. Because it's spread out and large, you would have very few waves per second. So it has a large wavelength and a small frequency. Okay, so the waves are big, but so they're not very frequent. The other end of the spectrum, I know that's pink, that's supposed to be red. You would have gamma. So gamma, not drawing that all the same height, but you get the idea, has a small wavelength, which means it has a high frequency, and that actually makes it quite dangerous, gamma. All right. In terms of the colours, I'm looking at the rainbow here. The colours of the rainbow, the red end of the spectrum is the red colour is longer, and then the purple is smaller. Okay, so I've not made it very good to explain that very well. So the electromagnetic spectrum goes from radio waves to gamma. Okay, long wavelength to short wavelength. the colours of the rainbow are within that too, and they have, red is a long wavelength and then purple is a short wavelength. So that's why I've used those colours here. So radio waves have a long wavelength, gamma rays have a small wavelength. Okay, so let's have, you don't need to know the ranges, okay? What you do need to know is their uses and how they're detected. Okay, so I'm just going to quickly run through those now. 1 second. So these are those electromagnetic waves written out. So we're just going to look at the uses of them. So radio waves are used for communications, okay? So we use them for radio, obviously. We use them for communication, walkie-talkies, things like that. Now they actually have very few dangers, so they're not very dangerous, so we can just leave that, and we don't really need any safety there either. In terms of microwaves, so microwave, we obviously use them for microwave ovens because they have a particular effect on, they heat water really well. They make water vibrate, which heats it up. We also use it for Bluetooth, and we also use it for I should put in radio waves. We use it for Wi-Fi. Okay, we also use it in mobile phones. Sorry, it must be frustrating you, my awful typing. Mobile phones, okay? So we use microwaves for that. Dangers of microwaves, they can, because they heat up water, so obviously a microwave oven is a very powerful microwave, so it can burn. Okay, Bluetooth and mobile phones, I mean, there's not been enough evidence, they've not been around for enough years to see if there's any long-term effects. So you don't really need to talk about whether they have any long-term effects, because we don't really know if they do or not, although there is some consideration as to whether they affect your cells because they have this heating effect on water, okay? So I'm just going to put they can burn if you use a powerful source. So things that your microwave has is it doesn't turn on unless you close the door. And it has that grid on the front. In fact, it would be much better if the metal grid wasn't there at all and it was a solid piece of metal. But you need to see what the food's doing, so it has to be a grid. So that reflects the microwaves. Okay. Now, infrared radiation. Infrared radiation is another term for heat, so anything that's hot. So we use infrared radiation for thermal imaging. We obviously use it for heating our homes. We can also use it for communication, so sometimes it's used in optical fibres. Occasionally. We use it for remote controls as well. So remote controls are obviously a very weak source because remote controls don't burn you, but we do use it for remote controls. Now, because infrared radiation is heat, obviously one of the problems with it is that it can cause burns, so we can just pop that on there. So for safety, we would not touch a hot surface for too long. Okay. Next, visible light. So visible light is those colours of the rainbow that I was talking about. So Richard of York gave battle in vain is how you would remember them. Richard of York gave battle in vain. Red, orange, yellow, green, blue, indigo, violet. So we use visible light obviously to see. So our eyes have evolved to detect this electromagnetic wave. We use it in cameras, for photos, and we use it in fibre optic cables. Okay, and the dangers, if it's bright, it can damage our eyes. Okay, so we wear sunglasses and avoid looking at bright lights. Okay. The next one is ultraviolet. So ultraviolet is just out of the visible light, so we can't really see it. We use it for we use ultraviolet lights to detect fraudulent banknotes. So normal banknotes have got like loads of like ultraviolet ink on them, so that we can use them to discover. So if you put them under a black light, you can see, or an ultraviolet light, sorry, you can see lots of different parts of it light up. So it's useful for that. We use it also to for those like security pens. So you can write your postcode on your piece of equipment at home, like a TV or something, and then if it's recovered after a robbery, the police know the postcode of the person who owns it. We also use it, it's used for, we use it in washing powder. So you put ultraviolet washing, very ultraviolet particles inside the washing powder. It makes the washing look much brighter and whiter. So we use it for brighter, whiter washing. Can't think of anything else. Apart from the fact that it's used for tanning. So you can get a suntan from it. So what a tan is it is when your skin detects that it's damaged from ultraviolet. It produces a chemical called melanin, and melanin has a dark colour. So the more melanin produced, the darker you go. So a tan is actually a sign of your skin trying to protect itself from the sun. And obviously different skin tones have different amounts of melanin. So some people, the darker the skin, the more protected they are actually naturally from the sun, because they've already produced that melanin, and it's that chemical that gives the skin tone. So one of the dangers is obviously that ultraviolet radiation can cause skin cancer. So even though if you have a dark skin tone you are more likely to be protected from the sun, it still actually can damage your skin cells enough to cause skin cancer, because it mutates the DNA of the skin cells, which leads to cancer. Okay? So safety, we use suntan lotion or sun protection spray. So it has an SPF, sun protection factor. Okay, what that does is instead of your skin absorbing the ultraviolet radiation, your sun lotion does instead. So even greater frequency here are X-rays. So we obviously use X-rays to scan luggage at the airport to detect drugs or any metal objects and bombs and things. We also use it to see inside the human body, so for medical imaging, because it is absorbed by different parts of the body, different amounts. So it's absorbed by bone, but it's not absorbed by skin, so you can see where your bones are. Problem with having X-rays is, again, because we're getting into this shorter wavelength, so higher frequency, it's dangerous. So it can cause cancer because it mutates cells. So that is why when you go to the hospital to have an X-ray, if there is anyone else in the room, they will stand behind the screen, which absorbs the X-rays. And actually, you can't actually have too many X-rays. So what the normal X-ray machine is fine. It's if you have something called a CAT scan or a CT scan. So a CAT scan or CT scan is like having lots of X-rays all in one go. So you can only have a certain number of those in a certain given time because of the amount of radiation from the X-rays. You can only have the risks start to outweigh the benefits of finding the problem using X-rays. So using it for medical imaging, you're trying to find a problem, but if you have too many, then you're increasing the risk of cancer. So the risk of the cancer outweighs the benefit of having the X-ray. Okay, so you limit their use as well. The last one is gamma. Gamma is the most dangerous of the electromagnetic waves. We actually use it for medical imaging again. It's called PET scans. But it is also used to kill cancer cells, so we use it in radiotherapy. And people ask, well, if it kills cancer cells, but it causes cancer, why would you use it? So it causes cancer because it mutates cells. When I say mutates cells, let me write that better, because the biologists will not be very happy with me. So it mutates DNA in the nucleus of a cell. And that mutation then causes the cancer, or can cause cancer. Let me just pop that in here. So those are all the same. So again, you need to limit the amount of gamma radiation you are subjected to. Thing is, if you've got cancer and you need radiotherapy, the risk of the cancer is greater than the risk of the radiotherapy, so you are better off having the treatment of the cancer, even though the treatment could lead to more cancer. And what they do is they use a machine so that the cancer is really targeted, but the rest of the areas receive a smaller dose, so that you're trying to limit that. So these are all the types of electromagnetic wave. You need to know them all, and you need to know the uses and dangers. Okay. So just a little bit about radio waves here. So radio waves are detected by aerials. So when radio waves are absorbed by an aerial, they create an alternating current inside this metal bit of the aerial. Okay. And that alternating current has the same frequency as the waves that you're producing, or that you're detecting. So the waves come in here, they produce an alternating current inside the aerial, which has the same frequency of the waves you're detecting. And then the waves will induce sort of oscillations within that electrical circuit, which then can be detected. So the frequency in the circuit basically changes with the current, and the radio can convert that then into different frequencies. If you're listening to the radio, it can convert it into the different frequencies of the sound. Okay. So basically, aerials work by absorbing the radio waves. They make an alternating current within the aerial, and the frequency of the alternating current changes depending on the frequency of the wave. Just wanted to show you the skin cancer aspect as well. So you can see here this person's a trucker, so you can see the effect that the skin cancer's had on their face. So this side of the face was always out towards the window. So you can see there that it causes, actually ultraviolet radiation causes premature aging of the skin because it damages those skin cells. You can see that effect here as well, the sun. You can see that melanin being produced here, so you've got the darker areas. So to protect against that, you should wear an SPF, and you should always wear an SPF on your face and hands, which are always in the sun, okay? Even if it's not really, really sunny outside. And then we just talked about, the fact that the darker your skin tone, the more melanin you actually naturally produce, and so you are more naturally protected. However, you can still develop skin cancer, so you need to wear sun lotion so that you're protected. Okay. And we also talked about gamma radiation. So gamma radiation, here this lady has had some radiotherapy. So you can see how the gamma radiation has damaged the skin cells on her neck and things, but obviously the treatment, that even though that would be uncomfortable, the treatment for the cancer is more important, or more, the treatment is it's important to treat the cancer because the risks from the cancer are greater than the risks from the cure from radiotherapy. Okay, so the benefits outweigh the risks. And we talked about microwave ovens as well. So microwave ovens only work when the door is closed. Okay, you can only switch them on when the door is closed. And then they have this grid at the front. It'd be better if this grid wasn't here. It's just that you need to see your food as well. And inside they've got lots of reflective surfaces here to reflect the microwaves back onto the food. The very last part of this is triple only. So if you're doing combined science, you don't need to worry about this. And it's just about lenses. So I did go through this with 11B1, so you probably are okay. I just quickly go through it with 11A1 if you want to. So lenses refract light, so they bend light, okay? So if you have a lens, it follows these rules. So these are the 3 rules it will follow. A parallel ray will go through the focal point. A ray that goes through the centre of a lens will not refract, and a ray that goes through the focal point will then go parallel. You actually only need to draw the first 2 lines of this. And the third one is actually helpful just to check you've got it in the right place. So I'll show you those 3 rules in action. So the focal point is where the rays would naturally come to, any parallel rays will refract through. So here's our lens, all of this line here is the lens, here is our object. These lines would not be drawn on, these are the answers to a question. I'm going to show you how to construct these lines. So a parallel ray, so that's this ray here, okay, will go through the focal point behind the lens, so that's here, okay. A ray that goes through the centre of the lens, so that's this one, through the middle, does not refract, so it's a straight line. And those 2 lines will meet at a point, and those are the only 2 lines you need to draw. You can draw the third one, and it will allow you to see if the other 2 are in the right place. And the third one is a ray that goes through the focal point. So this time to reflect the focal point in the front, which is the same distance away from the lens. So that one will then go parallel. So it goes parallel to this line in the middle, and this is where your image is formed. So when you draw the image, you draw a line down, okay? And that shows you your image line. So this is an object, this could be anything, it could be a person, it could be a tree, it could be anything here. And this is your image, so your image will form on this side of the lens. We can tell some things about this image. We can tell it's magnified because it is 1, 2, 3, 4, 5, 6 times bigger than this one. 1, 2, 3, 4. Not 6 times bigger, sorry. This one's 6 squares and this one's 4 squares. So its magnification would be the image height divided by the object height. This is 6 squares, this is 4. 6 divided by 4 is 1.5. Okay? We can also tell that the image is real. A real image is where the lines actually cross, so it is a real image. It is inverted because the line goes down from the middle line to here, so it's formed underneath, so it is inverted, so it's down, and it's magnified because it's bigger. Let's have a look at another example. So this is how a camera works. We just work it the same way. So the black lines won't be here, apart from you would have your object line here, and you will have your lens here. So parallel line, so this line will go through the focal point here on this side. A line that goes through the centre of the lens does not refract. So that's that one. Oh, I did the other one first, sorry. One that goes, the third rule is a line that goes through the focal point. So this one will then go parallel, which is there. And then the centre line does not refract. And remember, you actually only need these 2. The third one just allows you to figure out if you're in the right place. So what can we tell about this image? We can tell, so the object is quite far away from the focal point. So what we actually get is a smaller image. Well, that makes sense. If we take a photo on our phone camera, the image is smaller than the object we're looking at. So that makes sense, it's smaller. You can figure out how much smaller it is. We do the image height, 1, 2, 3, 4 squares, divided by the object height, which is 10 squares. So 4 divided by 10 is 0.4. So it's 0.4 times as big. We know it's inverted because the line is going down, so it's inverted. And we know it's real because the rays are really crossing at that. You can call it smaller, diminished means smaller. And then we can do a magnifying glass. So with a magnifying glass, your focal point is here and the object is inside the focal point. So this one's a bit strange. So I've actually drawn the first line already, sorry. So a parallel line will go through the focal point. So here's our focal point here. And now what happens is this ray, I'm going to talk about the dotted lines in a minute, so let's ignore the dotted lines. The next line is a ray that goes through the centre of the lens does not move. So that's that one. Does not refract, sorry. So that's that one. And you can see these rays are not going to meet. So what we do to make them meet, we need to pull the lines backwards and we draw some dotted lines here behind. We can see that they're meeting here. So we actually call this a virtual image because our real rays are not meeting on the right hand side of the lens. So we've made a virtual image on the left hand side by drawing our lines backwards. So this image is a virtual image, and we can see that the image is bigger than the object. Now if I was to put a piece of paper here, you would not get an image, okay, because it's a virtual image, it's not real. But if I was to put a piece of paper on the other ones, where the image is here, then I would see an image on that piece of paper. This is what I see. On this one, if you put a piece of paper here on the image, you won't see it because it's a virtual image. So your eye can see it, but you wouldn't get an image on a piece of paper. Magnification. So again, you've got your image height, which is 10, divided by your object height, which is 4, and 5. So 5 divided by 10. 10 divided by 5 is 2, so it's twice as big. Okay. So this image is virtual, it's upright because the line is going up, and it is magnified. This is quite a difficult one to do actually. So an image is virtual when it's formed where the vertical rays intersect. So a real image is formed where the real rays intersect. If you have a mirror, mirrors reflect light, so they reflect light through their focal point. So you can see a parallel line is reflected through the focal point, and a line through the focal point goes parallel. So you can see your image there. Let's do that again. A parallel line is reflected through the focal point. The focal point, one that goes through the focal point, is reflected parallel. And that's where your image is formed. And we can calculate the magnification. So it's the image height divided by the object's height. So 14 in this case divided by 10, which is 1.4. So this image is real, it's inverted, and it's magnified. So this is a little summary for you. Oh, no, that's not a good summary. Ignore that summary. We'll just go back to this. This is what you need to know. Those 3 rules. Remember, you only need the first 2, but the third one's a good check. These are the rules that are good rules to remember. Okay? Good. Okay, hopefully that's all been very useful to you. And, best